Today we are going to learn alternating series. Alternating series is an infinite series whose terms are alternate in sign. Whose terms are alternate in sign. Alternating series. Alternating series an alternating series is an infinite series. Series whose terms are alternate in sign. For example, summation n is equal to 1 to infinity minus 1 raised to n plus 1 upon n is equal to, if we put n is equal to 1, we obtain 1 upon 1. If we put n is equal to 2, we obtain minus 1 by 2. n is equal to 3, we obtain plus 1 by 3, minus 1 by 4, plus and so on, plus minus 1 raised to n plus 1 upon n, plus and so on. First term is positive, second is negative, plus, third is positive, fourth is negative, and so on. Number 2. Sigma n is equal to 1 to infinity minus 1 to the power n plus 1, which is equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. Alternating series is an infinite series whose terms are alternate in sign, plus minus or minus plus and so on. In alternating series, we prove the Lebanese theorem for alternating series. Theorem Lebanese theorem. Lebanese theorem. Statement: if sequence n is equal to 1 to infinity is a sequence of positive number, is a sequence of positive numbers, such that number first, a1 is greater than or equal to a2, a1 greater than or equal to a2, a2 greater than or equal to a3, and so on. an greater than or equal to an plus 1, and so on. an greater than or equal to an plus 1, and so on. That is, sequence n is equal to 1 to infinity is non-increasing. That is, sequence a suffix n is equal to 1 to infinity. and so on. That is, sequence an n is equal to 1 to infinity is non-increasing sequence. Is non-increasing sequence. Second one, limit n tends to infinity of an is equal to 0. Limit n tends to infinity of a suffix n is equal to 0. Then the alternating series. Then the alternating series. Summation n is equal to 1 to infinity minus 1 raised to n plus 1 into a suffix n is convergent. Is convergent. Sequence n is equal to 1 to infinity is sequence of positive numbers. Positive numbers. Proof of this theorem. Proof of this theorem. Since by hypothesis sequence n is equal to 1 to infinity is a sequence of positive numbers. Since by hypothesis sequence a suffix n is equal to 1 to infinity is a sequence of positive numbers. Positive numbers. Therefore, a suffix n is greater than 0 for all n belongs to I. Therefore, a suffix n is greater than or equal to 0 for every n belongs to I. Sequence an is sequence of positive numbers. Positive numbers. Therefore, a suffix n is greater than 0 for all n belongs to I. That is, a1 is greater than 0, a2 is greater than 0, an is greater than 0, an plus 1 is also greater than 0, and so on. And so on. We have the alternating series. Summation n is equal to 1 to infinity minus 1 to the power n plus 1 into an. We have the alternating series. Alternating series. Summation n is equal to 1 to infinity minus 1 to the power n plus 1 into an is equal to a1 minus a2 plus a3 minus a4 plus and so on, plus minus 1 raised to n plus 1 into an plus and so on. This is an infinite series whose terms are alternate in sign. Therefore, this is an alternating series. Let S suffix n is equal to a1 minus a2 plus a3 minus and so on plus minus 1 raised to n plus 1 into an for every n belongs to I. Sn is partial sum of the series summation n is equal to 1 to infinity minus 1 raised to n plus 1 into an minus 1 raised to n plus 1 into an. Now we write S1. S1 is sum of first term which is equal to A1, A suffix 1. Now we write S3. S3 is equal to sum of first three terms of the series. A1 minus A2 plus A suffix 3, which is equal to S1 minus A2 plus A3. S1 is A1. Therefore, S3 minus S1 is equal to minus A2 plus A3. Minus A2 plus A3 is equal to minus times A2 minus A3. A2 minus A3. A2 is greater than A3. A2 is greater than A3. Since by hypothesis 1, A1 is greater than or equal to A2, A2 is greater than or equal to A3. Since by hypothesis 1, since by hypothesis first, sequence an is non-increasing sequence. Sequence A suffix n is equal to 1 to infinity is a non-increasing sequence. Non-increasing sequence. That is, A1 is greater than or equal to A2, A2 is greater than or equal to A3, A3 is greater than or equal to A4, A4 is greater than or equal to A5, and so on. An is greater than or equal to An plus 1, greater than or equal to, and so on. Since A2 is greater than or equal to A3, since A2 is greater than or equal to A3, therefore A2 minus A3 is greater than or equal to 0. Therefore minus times A2 minus A3 is less than or equal to 0. Therefore, S3 minus S1, which is equal to minus A2 minus A3, which is less than or equal to 0. S3 minus S1, S suffix 3 minus S1 is less than or equal to 0. That is, S3 is less than S1. That is, S suffix 3 is less than or equal to S1. Or we say that S1 is greater than or equal to S3. This can be written as S1 is greater than or equal to S3. Similarly, S5, S suffix 5. Similarly, S suffix 5 is equal to A1 minus A2 plus A3 minus A4 plus A5, which is equal to S3 minus A4 plus A5. Therefore, S5 minus S3, S5 minus S3 is equal to minus A4 plus A5, which is equal to minus times A4 minus A5. But A4 is greater than A5. But A4 is greater than or equal to A5. Therefore, A4 minus A5 is non-negative, greater than or equal to 0. Multiplying by minus 1, we write minus A4 minus A5 is less than or equal to 0. Therefore, S suffix 5 minus S suffix 3 is equal to minus A4 minus A5, which is less than or equal to 0. S5 is S5 minus S3, S suffix 3 is less than or equal to 0. That is S suffix 5, S suffix 5 less equals S suffix 3, S suffix 3, S suffix 3. This can be written as S suffix 3 is greater than, S suffix 3 is greater than or equal to S suffix 5, S suffix 5. This is, say, An is greater than 0 is statement number 1, equation 1. This is, say, number 2. This is number 3. Similarly, we can write S suffix 5 is greater than S suffix 7. Similarly, we can write S suffix 5 is greater than, S suffix 5 is greater than or equal to S suffix 7. And so on. In general, we write S suffix 2n minus 1 is greater than or equal to S suffix 2n plus 1 for every n belongs to I. For every n belongs to I. 2. This is set 3. 3 and so on. And so on. Thus, and so on. Thus, from 2, 3 and 2, 3, 4. This is a 4. 5. From 2, 3, 4 and 5. And 5. S1 is greater than or equal to S3. S3 is greater than or equal to S5. S5 is greater than or equal to S7. Greater than or equal to and so on. Greater than or equal to S suffix 2n minus 1. Greater than or equal to S suffix 2n plus 1. Greater than or equal to and so on. Therefore, sequence S suffix 2n minus 1, n is equal to 1 to infinity, is non-increasing sequence, is non-increasing non-increasing sequence. This sequence is non-increasing sequence. This is say 6. Statement number 6. Non-increasing sequence. Now, S suffix 2n minus 1 is equal to A1 minus A2 plus A3 minus A4 plus A5 minus A6. A5 minus A6 plus and so on, plus last term is A suffix 2n minus 1 for every n belongs to I. For every positive integer n belongs to I. That is, A1, A3, A5 are positive, and this term is A1, A3, A5. These are odd terms. Odd terms are positive, therefore S suffix 2n minus 1 is also positive. We write S suffix 2n minus 1 is equal to A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus and so on, last but one term, that is A suffix 2n minus 3 minus A suffix 2n minus 2. Next is A suffix 2n minus 1. If we add 1, we obtain 2. If we add here 1, we obtain 2. Adding 2n minus 1, 2n minus 3 plus 1, we obtain 2n minus 2. Again, adding 1 in 2n minus 2, we obtain 2n minus 1. Sum of first 2n minus 1 terms. Since by hypothesis first, each bracket on RHS is positive, and by 1 sequence n is equal to 1 to infinity is sequence of positive term, therefore A suffix 2n minus 1 is also positive. Since by hypothesis 1, hypothesis first, A1 is greater than or equal to A2, A2 is greater than or equal to A3, A3 is greater than or equal to A4, and so on. Therefore, each bracket on RHS of 7 is positive. Therefore, each bracket on RHS of 7, right hand side of equation 7. Each bracket on RHS of 7 is positive, and by 1 n is greater than or equal to 0 for all n belongs to I. That is, A suffix 1 is positive, A suffix 2 is positive, A suffix 3 is positive, A suffix 2n minus 1 is also positive. By 1, A suffix 2n minus 1 is greater than 0. Therefore, we write S suffix 2n minus 1 is greater than or equal to 0. Therefore, sequence S suffix 2n minus 1 n is equal to 1 to infinity is bounded below. Bounded below. This sequence S suffix 2n minus 1 n is equal to 1 to infinity is bounded below. Bounded below. This is, say, 8. But we know theorem on monotonic sequences, theorem 3 on monotonic sequences. But we know theorem a non-increasing sequence, non-increasing sequence which is bounded below is convergent. This is 9. From 6, 8 and 9, from 6, 8 and 9, sequence S suffix 2n minus 1, n is equal to 1 to infinity is convergent to say L. Therefore, limit n tends to infinity of S suffix 2n minus 1 is equal to L. Similarly, sequence S suffix 2n n is equal to 1 to infinity is convergent to say capital M. By definition of convergent sequence, limit n tends to infinity of S suffix 2n minus 1 is equal to L, and limit n tends to infinity of S suffix 2n is equal to m. Now we prove L is equal to m, then sequence Sn and both subsequence converges to same limit, and hence sequence Sn n is equal to 1 to infinity is convergent. We claim L is equal to m. Now S suffix 2n is sum of first two n terms of the alternating series summation n is equal to 1 to infinity minus 1 raised to n plus 1 into an. That is a1 minus a2 plus a3 minus a4 plus and so on. Last term is a suffix 2n for every n belongs to I. For every positive integer n belongs to I. S suffix 2n is equal to a1 minus a2 plus a3 minus a4 plus and so on minus a suffix sum of first two n terms of the series. A suffix 2 even terms are negative, therefore a suffix 2n is negative. Last but one term is a suffix to n minus 1 minus a suffix to n. This is equal to s suffix to n minus 1 minus a suffix to n for every positive integer n, s suffix to n. Taking limit on both the sides as n tends to infinity. Taking limit on both the sides. Limit n tends to infinity of LHS. Limit n tends to infinity of s suffix to n is equal to limit n tends to infinity of RHS s suffix to n minus 1 minus a suffix to n. Applying theorems on limit, we write limit n tends to infinity of s suffix to n minus 1 minus limit n tends to infinity of a suffix to n. A suffix to n. This is say 10. From equation 10, limit n tends to infinity of s suffix to n is equal to m is equal to L minus 0 by theorem 3. Theorem 3 on convergence and divergence of series. Convergence and divergence of series. Therefore, m is equal to L. M is equal to L. Since limit n tends to infinity of a suffix to n is equal to 0. Is equal to 0. M is equal to L. Therefore, both subsequences s suffix to n minus 1, n is equal to 1 to infinity, and s suffix to n is equal to 1 to infinity, converges to same limit. Converges to same limit. L equals m. Therefore, sequence s suffix n is equal to 1 to infinity, converges. Therefore, sequence n is equal to 1 to infinity is convergent. Is convergent. Therefore, by definition of convergent series, corresponding alternating series, summation n is equal to 1 to infinity minus 1 raised to n plus 1 into an is convergent. Is convergent. Hence the proof of theorem. Hence the proof of theorem, Lebanese theorem. Hence the proof of Lebanese theorem. Thank you for watching the video.